Hello everyone, myself Dr. M.S. Vivek, Assistant Professor, working in Department of Chemical Engineering, Hindustan College of Engineering and Technology, Coimbatore. I am going to take a lecture on chemical reaction engineering. So, different topics on chemical reaction engineering will be discussed further in this video. Chemical reaction engineering is nothing but is the art of virtually every chemical process. It separates the chemical engineers from other engineers generally. So industries that draw heavy on chemical reaction engineering are chemical process industries like Dye, DuPont, Amco, Chevron, and other pharmaceutical and medical industries that forms any batch or continuous process or the chemical reactions that take place in the plant are driven by the chemical reaction engineering subject. So, to know the basic concepts of the chemical reaction engineering, we have to first know what is chemical kinetics. Chemical kinetics is nothing but it is the study of role at which the chemical reaction occurs and influences the process parameters like temperature, pressure, concentration on the rate of the reactions. The study of the chemical kinetics help in giving the idea regarding the reaction mechanism, speed of the chemical reaction, and the formulation of suitable rate expression which represents the given chemical reactions. So, the overview of chemical reaction engineering is nothing but treatment of any raw material or given raw material to a chemical treatment step, then moving into the physical treatment to produce a product. And the unreacted reactants are recycled to again back to the raw material stream, and again it is reacted with the new fresh stream to form the product. So, a reaction that is typically a chemical process, that is A plus B gives a product C. So, moving on to the chemical reaction, it is a process in which at least one species is transformed into the chemical different species. For example, combustion of methane. Let us see CH4 plus 2O2 gives CO2 plus 2H2O. So, here is the reaction where methane and oxygen is given carbon dioxide and water. So what a reactor can do is a performance equation that can be derived in the method of kinetics. So the contacting pattern or how materials flow through and contact each other in a reactor, how early or late the compasses of state of aggregation. By their very nature, some materials are very clumpy. So the input is given into the reactor, and after reaction time taking place, that is the reactant present inside the reactor known as residence time. So after the reaction is taking place, there is an output as a product where kinetics plays a major role. So how fast the reaction happens is studied in the kinetics. So this above figure shows the information about and predicts the reactor how they. So output is directly a function of input plus kinetics and the contacting time. That is the known as the reactor reaction. So why performance equation is important? Because with the expression we compare different design and conditions, find out the best and scale up the large units. So the reactors are divided into three different reactors. That is, one is batch reactor, second is continuous state tank reactor, this is generally known as CSTR, and third is plug flow reactor known as PFR. So this is the diagrammatic view of batch reactor, PFR and CSTR. There is a batch reactor where the input is given and the reactor is continuously mixed until the product is formed. In a plug flow reactor is a tubular reactor where the reactor is sent and the reactant is made to react in a tubular flow and product is taken place. In a continuous stir tank reactor, a continuous stirring is being maintained in the reactor and continuous flow is maintained. So batch reactor, as we have discussed in a brief, we have seen that batch reactor are stirrers or impellers are fitted into it. There is no inlet and outlet for a batch reactor. So directly the reactant is sent into the reactor and kept for a particular time. The composition is uniform in the reactor. The composition changes with respect to respective time actually in the batch. Whereas in a plug flow reactor and continuous state tank reactor, the difference in plug flow and continuous state tank reactors are there is no back mixing or axial mixing in the plug flow reactor. Whereas in continuous state tank reactor like CSTR, the impellers is fitted and there is a back mixing will be occurring. In PFR, it consists of a cylindrical tube, whereas in CSTR, there is a mixing of uniform and homogeneous liquids. And we see in the PFR there's an input and output stream is available, but in CSTR our steady state composition is same for both input and output. there is no back mixing in the PFR, whereas the CSTR there is an input and output stream is available. So the classifications of the reaction, the chemical reactions are decomposition reactions, combustion reactions, and isothermal reactions. And some of the examples that are being given here for all these three reactions. Also, the reactions are classified into two different categories, that is homogeneous reactions and heterogeneous reactions based on non-catalytic and catalytic reactions. Most of the gas phase reactions are homogeneous in non-catalysis, whereas in catalytic most are liquid phases, and their reaction is colloidal system and enzymatic, whereas in non-catalytic it is fast reactions such as burning of flame and such on. Some of the examples of heterogeneous reactions for non-catalytic are burning of coals, roasting of ores, act of solids with acids, gas liquid absorptions with reactions, and so on. Whereas for the catalytic, it is like ammonia synthesis, oxidation of ammonia, and so on. The variables that are affecting the rate of the reactions are in the homogeneous systems are temperature, pressure, and composition are generally, whereas in the heterogeneous systems or reactions there is addition of temperature, pressure, and composition with heat and mass transfer effects. So the definition of rate equations are based on the unit of volume of the reacting fluids. This Ri that is given as Ri is equal to 1 by V dNi by dt, where the dNi is moles of I formed divided by volume of the fluid into time taken for the reaction. Based on the unit mass of the solid in fluid solid systems, Ra dash is given as 1 by W dNi by dt, where it is considered in the mass. So moles of I formed divided by mass of solids divided into time. So based on the unit of interfacial surface of two liquids, Ra double dash will be given as 1 by S in terms of 1 by S, where it is given as surface. Whereas on based on unit volume of the solid in gas solid systems, it is given as Vs, where volume of solids have been taken. So based on the unit volume of the reactor, it is taken as VR, where it is denoted as volume of the reactor. So on this case, the reaction rate has been defined at different types. So from this equation, all is taken as a volume of fluid or mass of the solids. All are same at every conditions. The reaction rates are same. So, what is the rate of reaction? The rate of reaction is a measure of change of concentration of reactant or product over time at a particular time. So, the derivation for 2NO2 gas when converted into 2NO plus O2 is given here, where the rate of reaction is taken place here, and the units of rate for the homogeneous system is given as concentration per time or moles per volume or time. For the heterogeneous reaction, it is given as moles per area into time or surface concentration by time. So reaction rate is independent of size of the system. So how rate can be measured? At the beginning of the reaction, it is called initial rate. At any point of time, while the reaction is in progress, called instantaneous rate. Over the interval of time, which is called an average rate. So the reaction speed will be fast, slow, and moderate. So it is given in the cellular process here. And the reaction rate or rate of the reaction, it can be determined over particular time of interval or at a given point in time, and the rate of the reaction is measures of changes of the concentration of the reactant or product over time. So let us consider a reactant A plus A and A plus B gives R and SS. The most useful measure of the reaction rate of the reactant A is then given as the reaction rate minus RA is equal to minus 1 by V dNA by dt. The minus represented here is the disappearance of the reactant, and it is given in the unit of moles per meter cube per second. The rate respect to the stoichiometric coefficient is given as minus Ra by A is equal to minus Rb by B is equal to minus Rr by R is equal to minus Rs by S. So A, B, R, S are the stoichiometric coefficients here, and the Ca, Cb, Cr, and Cs are the concentrations of the different species. So the rate law of the rate equation or the rate equation, which is the mathematical representation of the dependency of the reaction rate with the change of concentration at a particular temperature, or an algebraic equation that relates minus Ra to the species concentration. It is generally known as kinetic expression on the rate law. So the rate law minus Ra is given as rate constant multiplied function with concentration. So the concentration is the function dependence on temperature terms. So the final output is a minus Ra is equal to Kca or k naught e power minus e by rt ca naught. So whereas the E here denotes the activation energy, R as gas constant and T as temperature dependent. So K represents, as I discussed earlier, the nomenclatures are discussed here. So with this, I would like to thank on the topic reaction kinetics and rate equation. Uh, so thank you everyone for describing the model on the chemical reaction engineering.